Thanks everyone for thank you for the invitation to speak. And yeah, so it's been great to come to the GBI event this week, and now the founding guide and meet all of you. It's been really lovely. I've really enjoyed it all. And this is my first time. And when I was accepted the invitation to come here, I was a little unsure of where GBI finished and founding guide started, but it's great to have that better now. And so I was a little, when I was going through a few weeks ago, going through it and realizing that I was going to talk at both the GI event and founding guide, I was like, oh, okay, what do I need to, what should I speak about at founding guide? So this is some work I've been doing on for quite a while. Never really found the right audience to do. So I hope you guys are the right one. Yeah, so in biomedical imaging space, the datasets we've been analyzing are really getting larger and larger. So whereas like 10, 15 years ago, people study might be like 30 or 40 subjects, now we're getting into the thousands. So the methodology that was developed or used those sort of smaller scales needs to be made more robust when we're dealing with such large numbers, particularly when we're looking to get clinical trials through the Australian Imaging Service and process the data. And so what we really want to be able to do is do sort of end-to-end processing, where take from the images that get acquired all the way quality control all the way through to actually producing the results to be analyzed. And so to this, we want to store the derivatives that are produced by the analysis alongside the original data. And this way they can be shared as well when we get to when they need to be published. So typically imaging data, biomedical imaging in particular, is stored in data trees. This is when the data goes into XNAT, it gets sorted first by project, and then subject, and then the session. So one object might come from multiple visits, longitudinal study, for example. And under that, you have the scans that live under that session. However, when we go to analyze form a statistical analysis in our scientific studies, we want the data in this tabular frame. So if we're going to do this end-to-end analysis, we need to sort of do this virtual mapping. So this is what Frametree aims to do. So the first step in doing this is to overlay virtual columns across the data tree. So here you can pick up the T1 weighted MRI image across each session. And so consider that like a regular expression of the resource name. And this conceptualization, the sessions themselves will form the rows of the data frame. So extending this concept further to the derivatives that are produced from the analysis, we not only have the source columns, but these sync columns here, which are sort of placeholders for where like intermediate derivatives, such as like a brain mask here, or these sort of output metrics, like white matter lesion volume, or the average gray matter thickness, which might then be sort of passed on to the actual statistical analysis. And so conceptualizing the analysis like this, and and storing the data back inside the repository as you are analyzing it allows the data set to be incrementally analyzed. This is quite important when it comes to large studies that might span multiple years. If you only go to analyze the data at the end of that 3 years, you may find there was some issue with the acquisition at some point, and data is no longer able to be analyzed, and so you've wasted a lot of money. So to be able to do at least the initial pre-processing steps as the data is acquired, and store that back in the repository so it can be QC'd, is quite important. So here we have, with these data columns, you can, all the rows, not all the rows need to be present. So this one's still just a placeholder, but for these two rows here, we might have already derived the mask for them. And the Frametree is also, you're also able to specify rows which maybe fail QC and then are omitted from your analysis for particular metrics, but still kept there for, just say, like there was an issue with your functional MRI, so you might be able to do an anatomical analysis, but not be able to perform the functional analysis. So not all the data or the derivatives that are derived, or even the input data sort of sits at the session level. Some of it sits at the subject level as well, such as like the age of the subject or the change in gray matter thickness between the first and second visit. And so if, in this case, the rows of the data frame have like a subject level frequency. And then you might even have some derivatives such as the average template, which is done across the whole data set. So this would be considered to have a single row in the sort of a data set level. And so then these data frame rows are sort of can be any combination of the categorical variables that you're using to across the sessions that are required, and can aggregate across multiple sessions here. So this is like all the visits for one subject, or all the subjects for a particular time point, or the whole data set, or in the case where you have a control and test group, you can also sort of slice along the group axis, or you might want to match up your, combine your age-matched control and test pairs. So the framework's able to sort of take any arbitrary combination of categorical variables and sort of map them onto this structure. So at this point, I forgive you for thinking, well, that's really nice, Tom. Why are you doing all that? But when it comes to actually analyzing data, once you've got this framework in place, you can then link these columns together, both the source and the sink columns, with pipelines, and sort of build up this chain of analysis from source to sink pipelines. And so just say you have this final derivative here that you want to calculate. When you request that, it will then sort of go back through the chain and push each of the pipelines that need to be executed onto an execution stack, and then execute them. But just say this derivative 2 has already sitting there within the repository, then at that point the pipeline 1 doesn't need to be run for that particular session. So this sort of enables common pre-processing derivatives, for example, surface meshes from anatomical scans, which get reused in multiple different types of analysis, to be reused. And particularly as a lot of these steps need manual QC, having them all in the central place where they could be QC'd once and then sort of automatically picked up is important. And then, provenance gets stored alongside the derivatives and gets checked to make sure that parameters that you're select and match up with the parameters that we use to create those previous derivatives. And so the definition of these columns and then the pipelines that run them gets defined within a JSON file, which gets sort of stashed away in the project level of the data set. And it can be specified using this Frametree command line tool that I've developed, but I'd really plan slash hope to write a simple UI that can be sort of integrated with XNAT, for example, to allow users to sort of set up these columns and analysis. And then note that all the parameters are stored alongside the pipelines within the frameset definition. So, for example, if you're wanting to run the analysis from multiple locations, say you're set up using Neurodesk and you've been analyzing it on your HPC, but then you want to switch to just analyze one subject locally, you can still pick up the same parameters and run them there. And yeah, another feature that we're working on is once we have these definitions in place, you have them in place before you acquire your data, you can then use to sort of make sure that all the right scans were acquired and pushed up successfully to the repository, and that the metadata checks out. And then each one of these columns gets assigned a file format, and this MIME type or MIME-like description by this file formats package that I've written, which also helps with that. It enables us to do some automatic conversion, so you can take inputs from multiple format types. So just to go in a bit more depth about this package, so it's a small package I've written, which is actually turned out to be quite useful, but it sort of it helps identify and handle different file types, and so it covers all the sort of all the official MIME types in the sort of INA repository, but it's also customizable for arbitrary formats, such as in biomedical imaging, we have nifty files with the JSON sidecar, JSON sidecar with extra metadata, and so it makes moving these around the the file system a lot easier, and it could easily be extended for more complex formats like ZAR that's been spoken about at this meeting. And then have the ability to map these file formats to this kind of MIME-like string, so give a specific format, a string representation of the format, and also create hooks to attach converters and also methods for reading and manipulating the files can be implemented in separate packages. So where this sort of links back, it's a bit of a roundabout way, but where it links back into ontologies is that one of the features added to this file formats was the ability to classify the contents of the file as well as the format. So this started off with things like zip, so saying that this is actually a zip file, but it contains a PNG. But for biomedical imaging, we've started extending this out to use the RADLEX ontology. So we come up with these sort of MIME-like definitions of what the contents of this. So this is a DICOM series with a T1 weighted MRI of the brain. So so not so much about adding new ontologies, but perhaps this is somewhere that we would look to record any ontological information for our XNAT data projects. So just like to thank people who've worked with me on this, Hakim, working together on the RADLEX, integrating RADLEX into the file formats, and people there at Sydney with